Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The intellectual currents of the mid-19th century presented a fertile, yet often bewildering, landscape for mathematicians. The very foundations of geometry, long considered settled by the Euclidean axioms, were being subtly reshaped by inquiries into non-Euclidean geometries and the intrinsic properties of curved surfaces. It was within this dynamic environment that Elwin Bruno Christoffel emerged, a scholar whose meticulous investigations would profoundly influence the trajectory of differential geometry and, by extension, our understanding of the universe itself. His early career, often overshadowed by his later, more celebrated contributions, reveals a mind already grappling with the profound challenges of describing geometric reality. Consider the prevailing understanding of surfaces at the time. While mathematicians like Gauss had brilliantly illuminated the concept of intrinsic curvature, the curvature inherent to a surface itself, independent of how it might be embedded in higher dimensional space, the tools for systematically exploring and quantifying these properties were still in their nascent stages. The challenge lay in developing a mathematical language capable of capturing the subtle ways surfaces could bend and twist, a language that could describe their geometry from within, rather than solely from an external, Euclidean perspective. This was the intellectual problem that Christoffel, even in his earlier work, began to address with a characteristic blend of rigor and geometric intuition. Christoffel's initial forays into mathematics revealed a deep engagement with a burgeoning field of potential theory. This branch of analysis, concerned with functions satisfying Laplace's equation, held significant sway due to its applications in physics, particularly in understanding gravitational and electrostatic fields. His doctoral dissertation, completed in 1956 under the supervision of Dirichlet, explored problems related to the distribution of heat and electric charge on surfaces. While seemingly an excursion into applied mathematics, this work laid crucial groundwork. The very act of describing these physical phenomena on curved manifolds necessitated a precise understanding of the geometric structure of those manifolds. It demanded a way to quantify distances, angles, and the rate of change of functions across these surfaces, problems that inherently required the development of sophisticated geometric tools. His early academic appointments, first as a private docent at the University of Berlin and later as a professor at the Eidgenössische Polytechnikum in Zurich, provided him with opportunities to refine these ideas. During this period, he began to articulate a more formal approach to the geometry of surfaces, expanding upon the descriptive power of Gauss's theorem egregium. The theorem egregium, a monumental achievement, demonstrated that the Gaussian curvature of a surface could be determined entirely from measurements made within the surface itself, using only the first fundamental form, the metric tensor. The means to systematically analyze the implications of this intrinsic curvature, particularly in relation to how curves and vectors behave on these surfaces, remained an area ripe for exploration. The problem that occupied many minds, and to which Christoffel would eventually provide seminal answers, concerned the generalization of concepts like straight lines and parallel transport to curved spaces. In Euclidean geometry, a straight line is the shortest path between 2 points, and parallel lines maintain a constant distance. On a curved surface, these notions become more complex. Geodesics, the shortest paths on a surface, are the natural generalization of straight lines. The question of how to define the parallelism of a vector as it is moved along a geodesic arises. If a vector is moved along a path on a curved surface without changing its direction relative to the surface itself, it remains parallel to its original orientation. This question, central to understanding the very fabric of curved spaces, required a new mathematical framework. Christoffel's early work was laying the conceptual groundwork for such a framework. He was deeply engaged with the differential calculus applied to functions of multiple variables and the geometry of curves and surfaces in three-dimensional Euclidean space. His publications from the late 1950s and early 1960s exhibit a growing focus on the differential properties of surfaces and the development of coordinate systems that could effectively describe them. He was concerned with how to express curvature in a way that was independent of the specific coordinate system chosen, a crucial step towards a truly intrinsic description. The mathematical tools available at the time, while powerful, often lacked the systematic organization needed to tackle these intricate geometric problems. Differential forms were being explored, and their full potential for describing curvature in a coordinate-independent manner was yet to be realized. Christoffel's approach, characterized by its careful attention to detail and its grounding in concrete geometric understanding, aimed to bridge this gap. He sought to build a rigorous calculus for curved spaces, one that could handle the complexities arising from the varying curvature of these spaces. This period was also marked by significant developments in the theory of invariance, the mathematical quantities that remain unchanged under certain transformations. In the context of differential geometry, invariants were essential for describing intrinsic properties. Christoffel's investigations implicitly contributed to this area by seeking methods to express geometric concepts in a manner that transcended the limitations of arbitrary coordinate choices. The intellectual lineage leading to Christoffel's major contributions is complex, drawing from the geometric insights of Gauss, the analytical rigor of Dirichlet, and the developing understanding of manifolds and differential forms. However, Christoffel's unique contribution lay in his ability to synthesize these disparate threads into a coherent and powerful new framework. He was forging new tools, driven by a deep-seated need to quantify and understand the fundamental nature of curvature. His early career, therefore, was an essential prelude, a period of intense intellectual gestation, where the problems were clarified and the foundational concepts were meticulously prepared for the groundbreaking synthesis that was to follow. His journey into the heart of differential geometry began with a profound engagement with a mathematical description of physical phenomena on curved surfaces, a testament to the interconnectedness of pure mathematics and its applications. The mathematical landscape of the mid-19th century was ripe for a revolution in understanding the intrinsic properties of curved surfaces. For centuries, geometry had largely concerned itself with shapes as they existed within a larger ambient space, typically the three-dimensional Euclidean world. The challenge that occupied many minds, a challenge Elwin Bruno Christoffel would profoundly address, was to delineate what could be known about a surface solely from within its own fabric, independent of any external embedding. This was a quest for intrinsic geometry. Christoffel's approach to this problem was deeply rooted in the foundational work of Carl Friedrich Gauss, particularly his groundbreaking memoir, Disquisitions generales circa superficies, curves. Gauss famously demonstrated that certain geometric properties of a surface, such as its Gaussian curvature, could be determined entirely from measurements made on the surface itself, using the metric tensor. This metric tensor, a mathematical object that captures the infinitesimal distances between points on the surface, became the central object of study for those seeking an intrinsic understanding. Gauss's methods, while revolutionary, left avenues for deeper exploration and generalization, particularly in how to systematically describe the variation of geometric quantities across the surface. The problem Christoffel tackled was how to quantify the very essence of curvature in a manner that was invariant, meaning it did not change if the surface was bent or deformed in a way that preserved its internal distances. He sought to develop a comprehensive framework for the differential geometry of surfaces. This required a rigorous understanding of how distances and angles are measured on a curved surface, a task elegantly captured by the metric tensor, often denoted in modern notation as G sub h. This tensor, essentially a matrix of coefficients, encodes how infinitesimal displacements in surface coordinates translate into actual distances. Christoffel's unique solution involved a meticulous analysis of the first and second fundamental forms of a surface. The first fundamental form, derived directly from the metric tensor, describes the intrinsic geometry, the lengths of curves, and the angles between them. The second fundamental form, on the other hand, relates to how the surface is embedded in the surrounding space, capturing information about its bending and twisting. The genius of Christoffel's work lay in his insight that the intrinsic curvature, a property independent of embedding, could be directly computed by relating these two fundamental forms. He developed explicit formulas that allowed for the calculation of Gaussian curvature, a pivotal measure of a surface's local shape, using only the components of the metric tensor and their derivatives. Consider a surface parameterized by two variables, say u and v. The first fundamental form defines the infinitesimal squared distance, ds squared, between two nearby points on the surface as a quadratic form. ds squared equals g sub 11 do squared plus 2 g sub 12 do dv plus g sub 22 dv squared. Here, g sub 11, g sub 12, and g sub 22 are the components of the metric tensor functions of u and v. These components are the key to understanding all intrinsic geometric properties. Christoffel's profound contribution was to show how to derive the Gaussian curvature, k, from these g sub h components. His derivation involved calculating the coefficients of the second fundamental form, which describe a surface's curvature in the ambient space. These coefficients, in turn, are related to the second partial derivatives of the surface's embedding functions. Christoffel's brilliance lay in finding a way to express the Gaussian curvature purely in terms of the metric tensor of the first fundamental form and its derivatives. This was a significant leap, as it meant that one could understand a surface's intrinsic curvature without knowing how it was embedded in a higher dimensional space. The curvature was an inherent property of the surface itself, discoverable from its internal measurements. The specific formulas Christoffel derived were intricate, involving partial derivatives of the metric tensor components. For instance, the Gaussian curvature k could be expressed as a complex rational function of the g sub h and their first and second partial derivatives. While the explicit form of these formulas is quite involved, their conceptual significance is immense. They provided a systematic and complete method for calculating the intrinsic curvature of any surface, given its metric. This was a powerful tool for mathematicians and physicists alike, offering a way to analyze the geometry of any curved manifold without reference to an external embedding. The modern relevance of Christoffel's work on the differential geometry of surfaces is profound and pervasive. The concepts he solidified form the bedrock of modern differential geometry and had extended far beyond the study of two-dimensional surfaces. The idea of an intrinsic curvature, calculable from a metric tensor, is central to Einstein's theory of general relativity, where spacetime itself is described as a curved manifold whose geometry dictates the motion of objects. The formulas he developed for calculating Gaussian curvature from the metric tensor are still taught as fundamental principles, serving as a gateway to understanding more complex geometric concepts. His rigorous approach to defining and manipulating geometric quantities on curved spaces laid the groundwork for the development of tensor calculus. The foundational understanding of how to differentiate geometric objects on curved manifolds was being forged here. Its focus on the metric tensor as the primary object of study from which all intrinsic geometric properties could be derived established a paradigm that continues to guide research in geometry and physics. Christoffel's meticulous development of these formulas provided the essential mathematical language and tools necessary to describe the shape and curvature of surfaces in a way that was both abstractly elegant and practically applicable, forever altering the course of geometric inquiry. The challenge of describing geometry on surfaces and in spaces that deviate from the familiar flatness of Euclidean geometry presented a profound intellectual hurdle. For centuries, mathematicians had grappled with the intricacies of curvilinear coordinates, recognizing their necessity for representing curved objects, but struggling with a consistent framework for performing calculus operations within these systems. The very notion of differentiation, so fundamental to understanding change in motion, became problematic when the coordinate axes themselves were not fixed, perpendicular, and uniformly scaled. Imagine trying to measure the rate of change of a quantity along a curved path using rulers that are themselves bending and twisting with the path. The standard rules of calculus, predicated on a stable Cartesian grid, faltered. Elwin Bruno Christoffel provided a revolutionary solution to this quandary through the introduction of what are now universally known as Christoffel symbols. These are more than mere notational devices. They are coefficients that precisely quantify how the basis vectors of a curvilinear coordinate system change from point to point. In essence, they capture the twist and stretch inherent in the coordinate grid itself. When one moves from one point to another in a curved space, the directions represented by the coordinate axes can change relative to each other. The Christoffel symbols, as three index quantities, encode the components of this change. For a coordinate system denoted by variables such as x1, x2, and x3, the Christoffel symbols, often represented using the Greek letter gamma, such as gamma sub hk, specify how the basis vector corresponding to the kth direction changes as one moves along the ith coordinate direction, influenced by the jth coordinate. This innovation was instrumental in developing the concept of covariant differentiation. Before Christoffel's work, differentiating a vector field in a curved space presented ambiguity. A vector field assigns a vector to each point on a surface or within a space. To comprehend how this field changes, one must compare vectors at infinitesimally separated points. These vectors, however, reside in different tangent spaces. Subtracting their components within a given coordinate system proves insufficient, as coordinate systems and their basis vectors are themselves in flux. Covariant differentiation, facilitated by the Christoffel symbols, offers a method for performing this comparison meaningfully. It produces a new vector representing the intrinsic rate of change of the original vector field, independent of the chosen coordinate system. The process entails taking the partial derivative of the vector's components with respect to each coordinate and subsequently incorporating correction terms that involve the Christoffel symbols. For a vector field v, whose components are v to the power of I, its covariant derivative with respect to the coordinate x to the power of j, represented as v to the power of I semicolon j, is calculated as the partial derivative of v to the power of I with respect to x to the power of j, augmented by a summation over k of the Christoffel symbol gamma to the power of I, kj, multiplied by v to the power of k. This formula, though appearing intricate, effectively accounts for the variation in the coordinate basis. The summation, denoted by a repeated index k, aggregates contributions from all possible directions, ensuring the resulting derivative accurately reflects change within the space's geometry. The importance of this advancement is profound. It's applied the fundamental mathematical tools for extending differential calculus from flat Euclidean spaces to general curved manifolds. This constituted a crucial stride toward understanding the intrinsic geometry of any space, irrespective of its potential embedding within a higher dimensional space. Christoffel's attention centered on intrinsic properties, those measurable and comprehensible by an observer confined to the space itself, without recourse to any external embedding. The Christoffel symbols, derived from the metric tensor of the space, which defines distances and angles, allowed for the calculation of these intrinsic geometric quantities. The metric tensor, often represented by g sub h, is the cornerstone of differential geometry. It dictates the geometry of the space by providing a rule for calculating the infinitesimal distance between two nearby points. From the metric tensor, Christoffel derived his symbols, revealing a deep connection between the metric structure and the calculus of vector fields on the manifold. This established a powerful paradigm. The metric tensor contains all the information about the space's geometry, and from it, one could derive all fundamental geometric concepts, including curvature. His work demonstrated that the Christoffel symbols act as the connection coefficients for the Levi-Civita connection, the unique torsion-free connection compatible with metric. This meant that the Christoffel symbols provided a way to connect tangent spaces at different points, enabling the parallel transport of vectors and the consistent differentiation of geometric objects. The intellectual lineage of this work traces back to the geometry of surfaces developed by Gauss. but Christoffel elevated these ideas to a much higher level of abstraction and generality. He provided a systematic and rigorous framework that could be applied to spaces of any dimension. His meticulous calculations and the clarity of his formulation provided the foundational tools for the subsequent development of tensor calculus, a language that would prove indispensable for fields ranging from differential geometry to general relativity. The Christoffel symbols themselves, as coefficients of the connection, are not tensors. They transform in a specific way under coordinate changes. However, they are instrumental in constructing tensorial quantities, such as the curvature tensor, which are invariant under coordinate transformations and truly represent intrinsic geometric properties. Christoffel's contribution was to provide the indispensable bridge, the calculational engine, that allowed mathematicians and physicists to move from the abstract definition of a metric to the concrete description of geometric behavior in any manifold. His work offered a profound insight into how curvature influences the very fabric of space, paving the way for a deeper understanding of the universe itself. The exploration of space's geometric character, particularly its intrinsic curvature, presented a profound intellectual challenge in the mid-19th century. While surfaces in three-dimensional Euclidean space offered tangible models for studying curvature, the aspiration to quantify the geometric properties of more abstract, higher dimensional manifolds demanded a more rigorous and general framework. Within this intellectual milieu, Elwin Bruno Christoffel's work on the curvature tensor emerged, providing the essential mathematical machinery to describe how spaces deviate from Euclidean flatness, building upon the foundation of the metric tensor, which encodes the local distances and angles within a manifold, and the covariant derivative, which allows for the differentiation of vector fields in a coordinate-independent manner. Christoffel's crucial insight lay in demonstrating how these elements could be combined to reveal the intrinsic curvature. The problem was to find a quantity that intrinsically characterized the curvature of a space, a quantity that would remain unchanged regardless of the coordinate system employed to describe it. This quantity needed to capture the fundamental geometric nature of a manifold itself, independent of any embedding into a higher dimensional space. Christoffel's unique solution was the development of the components of what is now known as the Riemann curvature tensor. This tensor, a sophisticated mathematical object, is constructed from the Christoffel symbols, which themselves are derived from the metric tensor. The Christoffel symbols, often denoted by gamma sub ijk, represent the coefficients of the connection. They quantify how vectors change when parallel transported along curves within the manifold. While these symbols transform in a specific, well-defined manner, they are the indispensable building blocks for constructing quantities that are invariant. The elegance of Christoffel's approach was in showing that the Riemann curvature tensor, formed by taking a specific combination of second partial derivatives of the metric tensor and terms involving the Christoffel symbols, possessed the property of coordinate invariance. This meant that the components of the curvature tensor, irrespective of the chosen coordinate system, would always represent the same intrinsic geometric property of the manifold. The tensor's components encode the extent to which parallel transport of a vector around an infinitesimal closed loop results in a change in the vector. In flat spaces, parallel transport of a vector around any closed loop returns the original vector unchanged. In curved spaces, the vector changes, and the Riemann curvature tensor quantifies this change. When a vector is moved parallelly along two distinct paths connecting the same start and end points, its final orientation depends on the path taken in a curved space, whereas it remains consistent in a Euclidean space. The Riemann curvature tensor quantifies this path dependency. The components of the Riemann curvature tensor, often represented as R sub ijkl, are derived from the metric tensor and its spatial variations. The formulation for these components, while intricate, directly shows how curvature arises from the spatial variation of the metric. It includes terms like the partial derivative of a Christoffel symbol with respect to a coordinate, combined with products of Christoffel symbols. For instance, a component can be expressed as the partial derivative of gamma sub ijk with respect to x sub l minus the partial derivative of gamma sub ilk with respect to x sub j, plus terms involving the product of gamma symbols, such as gamma sub mjl times gamma sub imk, minus gamma sub mil times gamma sub imj. This expression, when simplified and transformed covariantly, yields the components of the Riemann curvature tensor. The significant value of this development lies in its broad applicability. Christoffel's approach allowed for the calculation and description of the intrinsic curvature of any manifold, regardless of its dimension or whether it could be visualized within a higher dimensional Euclidean space. This marked a fundamental departure from earlier geometric methods that often relied on intuitive surface visualizations. The curvature tensor provided a purely algebraic and analytical way to study the geometry of space itself. It offered a means to determine if a space was flat or curved, and to measure the degree and nature of that curvature. The historical consequence of this innovation was substantial. It supplied the foundational lexicon and instruments for the developing discipline of differential geometry. Mathematicians could now rigorously study the geometric properties of abstract spaces, leading to deeper insights into topology, analysis, and the very nature of space and geometry. The invariance of the curvature tensor under coordinate transformations meant that it truly represented an intrinsic property of the manifold, a geometric fact, independent of how one chose to describe it. This concept of intrinsic properties, measurable from within the manifold itself, was a cornerstone for future geometric investigations. The enduring relevance of Christoffel's work on the curvature tensor is undeniable. It remains the fundamental mathematical object used to describe the curvature of Riemannian manifolds. Its components are taught in advanced geometry courses worldwide, forming the bedrock for understanding curved spaces. Christoffel's rigorous development of the curvature tensor provided the indispensable foundation for later breakthroughs, most notably in Albert Einstein's theory of general relativity, where the curvature of spacetime is the very manifestation of gravity. Christoffel's mathematical framework allowed physicists to translate the abstract concept of curved space into concrete, calculable quantities that could describe the behavior of the universe. His contribution was a conceptual leap that opened up new vistas in our understanding of the geometric structure of reality. Christoffel's intellectual journey extended into the realm of potential theory, a field deeply intertwined with electromagnetism, fluid dynamics, and gravitation. Mathematicians and physicists in the mid-19th century focused on how physical quantities like electric charge or mass influence their surroundings, creating a potential field. This potential field, often represented by scalar functions, dictated the forces experienced by other charges or masses. Early work by Poisson, Gauss, and Green had established foundational concepts, developing ideas such as the potential integral and the relationship between potential and charge distribution. A more geometrically detailed understanding of these potentials, especially for complex shapes and configurations, continued to be an active research area. Christoffel applied the same analytical rigor to these problems that he used in his differential geometry work. He investigated the properties of potential functions, particularly their connection to the geometry of the surfaces and regions where these potentials were defined. A significant aspect of his research involved the concept of capacity, a geometric property of a conductor that measures its ability to hold electric charge for a given potential. The capacity for a simple sphere is readily calculated, while the problem becomes considerably more difficult for intricate shapes, demanding sophisticated integration techniques and a thorough understanding of boundary value problems. Christoffel's approach frequently involved representing potentials through integral formulas, connecting the potential at a point to the distribution of sources or charges across a region. These integral representations offered profound insights into the geometric nature of potential fields, serving as computational aids. He explored how the shape and conductivity of a domain affected the behavior of the potential function within it. For example, he studied the problem of determining the potential within a region given the potential on its boundary, a classic boundary value problem with direct applications in electrostatics and heat conduction. His work established a more rigorous basis for understanding the connection between the geometric properties of a region and the solutions to Laplace's equation, the fundamental differential equation governing potentials in charge-free regions. Laplace's equation, expressed in Cartesian coordinates as the sum of second partial derivatives of a function with respect to each coordinate equaling 0, implied a smoothness and regularity for potential fields. Christoffel's contribution involved examining how this smoothness was affected by the underlying geometry and how integral representations could capture these geometric dependencies. Christoffel's investigations explored how a surface's curvature influenced potential distribution. He employed integral formulas to express potential at a point using integrals over the region's boundary. Careful analysis of these integrals revealed the influence of geometric features like a surface's principal curvatures on a potential field. This represented a significant advance toward a geometrically intuitive understanding of physical phenomena, complementing analytical treatments. The capacity of a surface, a key concept in electrostatics, received considerable attention. Christoffel's work established methods for calculating this capacity for bodies of arbitrary shape, linking it to solutions of specific integral equations. Capacity is closely tied to an object's geometric structure. A more spread out or complex shape may possess a different capacity than a compact one, even if they enclose the same volume. Christoffel's mathematical framework offered tools to quantify these geometric influences. His potential theory investigations also addressed harmonic functions, solutions to Laplace's equation. He examined properties of harmonic functions, including their representation by convergent series and their behavior near singularities. This exploration served a practical purpose, aiming to understand the physical behavior of fields in diverse scenarios, such as electric charge distribution or ideal fluid flow. Christoffel's methods frequently involved advanced techniques from calculus of variations and integral equation theory. He skillfully manipulated complex integrals, deriving precise relationships between geometric quantities and differential equation solutions. His approach emphasized providing a robust mathematical foundation for physical theories, ensuring well-defined concepts and rigorously established properties. Christoffel's enduring legacy in potential theory lies in its contribution to a powerful mathematical framework for describing physical phenomena. The integral formulas he derived, while potentially refined or superseded by more general methods in modern physics, embody the fundamental principle of connecting geometric properties to the behavior of potentials, a cornerstone of many fields. His work bridged the gap between abstract mathematical analysis and tangible physics, providing tools and insights that continue to inform our understanding of the physical world. The capacity of a surface, the behavior of harmonic functions, and the integral representations of potentials all owe a significant debt to his meticulous and insightful investigations. Our exploration will now turn to how these profound mathematical ideas, forged in 19th century Germany enter the broader scientific discourse and influence the trajectory of mathematics and physics for generations. We will examine the reception of his work and trace the lineage of his concepts as they were adopted, generalized, and transformed by subsequent generations, laying the groundwork for revolutionary advancements. Elwin Bruno Christoffel's intellectual architecture, though profoundly impactful, required diligent hands to extend its framework and integrate its sophisticated elements into the wider edifice of scientific understanding. The dissemination and assimilation of his abstract geometric concepts presented a unique challenge, demanding comprehension and a creative reinterpretation to unlock their latent power for physical applications. This process of intellectual inheritance and development testifies to the enduring strength of foundational mathematical ideas. Christoffel's exploration of differential geometry and the intrinsic properties of spaces provided a new lens through which mathematicians could view geometric relationships. This perspective, emphasizing coordinate-independent descriptions, offered a departure from earlier methods often tied to specific coordinate systems. The development of the covariant derivative, a concept intrinsically linked to Christoffel's work on parallel transport and curvature, offered a powerful tool for describing how geometric quantities change across a manifold. This was an essential step towards a more unified and elegant understanding of space itself. The problem of how to rigorously articulate and manipulate these intrinsically defined geometric quantities occupied many minds in the late 19th century. Christoffel's own meticulous work laid the groundwork, but the full potential of his approach was realized through the efforts of others who embraced and expanded upon his insights. The challenge lay in translating the abstract elegance of his formulations into a practical calculus capable of describing physical phenomena. This required a deeper engagement with the algebraic structures that underpinned his geometric constructions. One of the most significant pathways for the reception and extension of Christoffel's ideas emerged through the work of Gregorio Ricci-Carbastro. Ricci, deeply impressed by the geometric insights presented by Christoffel, embarked on a systematic study of the differential invariance of curves and surfaces. He recognized the need for a coherent algebraic framework to handle the complex relationships Christoffel had uncovered. Ricci formalized and systematized the manipulation of these geometric objects, developing what would become known as tensor calculus. This provided the essential machinery to operate with Christoffel's concepts in a general and consistent manner. Ricci's development of covariant differentiation, building upon Christoffel's earlier work, allowed for the consistent definition of derivatives of vector and tensor fields on curved manifolds. This enabled a precise description of how these fields change as one moves across the curved surface or space. The introduction of what are now known as Christoffel symbols representing the components of the connection that defines parallel transport became a fundamental element in Ricci's tensor calculus. These symbols, derived from the metric tensor, encapsulate the way in which the coordinate system itself warps the space, dictating how vectors change under parallel transport. The problem Christoffel had implicitly addressed was how to define a consistent notion of differentiation on a curved manifold, a task that is inherently problematic when relying on coordinate representations. The Christoffel symbols provided a way to express this covariant derivative in terms of coordinates, the true significance lying in their role as coefficients of the connection, independent of any specific coordinate choice. This independence allowed for the formulation of geometric laws that were invariant under coordinate transformations. The collaboration and intellectual exchange between Ricci and his student Tullio Levi-Civita further solidified and extended these ideas. Levi-Civita played a crucial role in refining the formalism of tensor calculus and exploring its deeper implications. He introduced the absolute differential, a coordinate invariant differential operator, and further developed the understanding of curvature through the Riemann curvature tensor, a construct that elegantly encoded the intrinsic curvature of a manifold using the Christoffel symbols. This tensor, built from the metric and its derivatives through the Christoffel symbols, provided a complete description of the local geometric properties of a space. The problem these mathematicians were effectively solving was how to move beyond local, coordinate-dependent descriptions of geometry to a global, intrinsic understanding. Christoffel's work provided the foundational tools for this shift, and Ricci and Levi-Civita provided the systematic algebraic framework to wield them. Their development of tensor calculus offered a powerful language capable of expressing geometric and physical laws in a manner that was independent of the observer's chosen reference frame. This was a significant conceptual leap, moving mathematics towards a more fundamental and universal description of reality. The reception of Christoffel's work was a gradual process of assimilation and extension. While his original papers might have been highly technical and perhaps accessible to a select group of mathematicians, the subsequent work of Ricci and Levi-Civita acted as a powerful conduit, translating his abstract insights into a more broadly applicable mathematical language. The development of tensor calculus provided the necessary tools for physicists to begin exploring the geometric nature of physical forces. The influence of Christoffel's ideas, filtered and amplified through the lens of tensor calculus, proved to be profoundly influential for the development of 20th century physics. The challenge of describing gravity, a force that seemed to permeate space itself, found a natural home within the framework of differential geometry. The abstract notions of curvature and parallel transport, which Christoffel had so meticulously investigated, provided the conceptual and mathematical bedrock for Albert Einstein's general theory of relativity. Einstein's revolutionary insight was to propose that gravity is a manifestation of the curvature of spacetime. The paths of objects through spacetime, he posited, are determined by this curvature, which is itself influenced by the distribution of mass and energy. To mathematically articulate this theory, Einstein required a sophisticated geometric framework capable of describing curved four-dimensional spacetime and the motion of objects within it. The tensor calculus, with its roots firmly planted in Christoffel's work on differential geometry, provided precisely this framework. The Christoffel symbols representing the connection coefficients became central to Einstein's field equations. They described how spacetime is curved by the presence of mass and energy, and how this curvature dictates the paths of objects. The geodesic equation, which describes the path of a freely falling object in spacetime, is formulated using these symbols. The development of tensor calculus, stemming directly from Christoffel's foundational investigations into parallel transport and curvature, enabled the mathematical formulation of general relativity. The problem of understanding the gravitational interaction was transformed from a question of forces acting across distances to a geometric problem of understanding the intrinsic structure of spacetime. Christoffel's contribution, therefore, was the introduction of specific mathematical objects and a fundamental shift in the way mathematicians and physicists conceived of space and geometry. He provided the conceptual tools that allowed for the description of a universe where geometry itself is dynamic and intertwined with matter and energy. The lineage of ideas from Christoffel's abstract geometric explorations to the sophisticated tensor calculus developed by Ricci and Levi-Civiter and subsequently adopted by Einstein illustrates a powerful dynamic in scientific progress. Foundational mathematical work, even if initially abstract, can provide the indispensable language for future scientific breakthroughs. Christoffel's meticulous development of concepts related to curvature and parallel transport offer the essential mathematical scaffolding upon which one of the most profound theories of the 20th century was built. The enduring significance of his work lies in this ability to provide the conceptual and computational tools that enable deeper insights into the fundamental nature of the universe. Elwin Bruno Christoffel's profound contributions represent a pivotal moment in the evolution of mathematical thought, particularly in the fields of geometry and analysis. His work provided the essential conceptual framework and computational tools that would later prove indispensable for describing the physical universe with unprecedented accuracy. The interconnectedness of his developments in differential geometry, tensor calculus, and potential theory reveals a unified vision, one that moved beyond the limitations of Euclidean space to embrace the complexities of curved manifolds. This conceptual leap facilitated a fundamental shift in how mathematicians and physicists understood space and its inherent properties, transitioning from local descriptions to the recognition of intrinsic, coordinate-independent characteristics. The enduring legacy of Christoffel's endeavors resides in his capacity to furnish the abstract, mathematical language that became the bedrock of 20th century physics, most notably Albert Einstein's revolutionary theory of gravity, and continues to shape modern geometric analysis and theoretical physics. Christoffel's early investigations into the properties of curves and surfaces laid the groundwork for a more sophisticated understanding of geometry. His exploration of geodesics, the shortest paths between 2 points on a curved surface, and his work on the curvature of surfaces, including the development of the Gaussian curvature, demonstrated an intuitive grasp of intrinsic geometric properties. These were explorations that delved into the very essence of spatial relationships. The problems of his time included a desire to quantify and understand the deviations from Euclidean geometry that arose in curved spaces. Christoffel's unique solution lay in his development of differential methods that allowed for the calculation of these geometric properties in a rigorous and systematic way. His approach provided a means to characterize the curvature of a surface at any given point, a crucial step towards a general theory of curved spaces. The development of the Christoffel symbols, a concept that bears his name, represents the cornerstone of his legacy. These symbols, derived from the coefficients of the first fundamental form of a surface, quantify how the coordinate system changes from point to point. In essence, they capture the twisting or bending of the coordinate grid itself within a curved space. The problem Christoffel addressed was how to define and manipulate quantities like derivatives and integrals in a way that was independent of the chosen coordinate system. His solution was to introduce these coefficients, which effectively encode the geometric information of the manifold. This allowed for the formulation of covariant differentiation, a method of taking derivatives that respects the curvature of the space. The modern relevance of the Christoffel symbols is immense. They are fundamental to the definition of a Riemann curvature tensor, the central object in differential geometry that fully characterizes the curvature of a manifold. They are taught in every graduate course on differential geometry and are implicitly present in virtually all applications of the field. Christoffel's engagement with potential theory further solidified his place in the history of mathematics. His work on Dirichlet's problem, which concerns finding a harmonic function satisfying given boundary conditions, contributed to the understanding of Laplace's equation and its solutions in various domains. The problems of his era included understanding the behavior of physical quantities like electric and magnetic potentials and heat distribution, which were often described by solutions to Laplace's equation. Christoffel's investigations provided deeper insights into the existence and properties of these solutions, particularly in regions with complex boundaries. His approach involved intricate analysis and the development of new techniques for dealing with boundary value problems. The modern relevance of potential theory is seen in its applications across physics, including electromagnetism, fluid dynamics, and elasticity, as well as in fields like probability and finance. The synthesis of Christoffel's work on differential geometry and potential theory revealed a powerful synergy. His geometric insights provided the context for understanding how potentials behave in curved spaces, and his analytical tools offered methods for solving the associated differential equations. This interconnectedness represented a developing unified perspective on the nature of space and physical phenomena within it. The abstract geometric concepts he formulated, such as the notion of parallel transport, the idea of moving a vector along a curve in a way that keeps it parallel to itself in the context of the curved space, provided a conceptual language for understanding how geometric properties evolve across a manifold. The true magnitude of Christoffel's contribution became fully apparent with the advent of Einstein's theories of relativity. Einstein, grappling with the challenge of describing gravity not as a force acting across space, but as a manifestation of the curvature of spacetime itself, found in Christoffel's work the precise mathematical tools he needed. The Christoffel symbols, along with the broader framework of tensor calculus that built upon them, allowed Einstein to formulate the Einstein field equations. These equations, which relate the geometry of spacetime to the distribution of matter and energy, are expressed using tensors and their covariant derivatives, concepts deeply rooted in Christoffel's research. The problem Einstein faced was how to mathematically express the idea that mass and energy warp spacetime, and that this warping dictates the motion of objects. Christoffel's symbols provided the crucial components for constructing the Riemann curvature tensor, which quantifies this warping. Their modern relevance is therefore confined to pure mathematics. They are the very language through which we understand the universe at its most fundamental level, governing everything from the orbits of planets to the expansion of the cosmos. The enduring significance of Christoffel's work lies in its ability to provide the conceptual and computational tools that enable deeper insights into the fundamental nature of the universe. His meticulous development of concepts related to curvature and parallel transport offered essential mathematical scaffolding upon which one of the most profound theories of the 20th century was built. This provided a rigorous framework for thinking about geometry in a way that was intrinsically tied to the properties of the space itself, independent of any external reference frame. This shift in perspective was revolutionary, moving mathematics towards a more abstract and fundamental understanding of space and its inherent structure. The lineage of ideas, from Christoffel's abstract geometric explorations to the sophisticated tensor calculus developed by Gregorio Ricciardo and Tullio Levi-Civita, and subsequently adopted by Einstein, illustrates a powerful dynamic in scientific progress. Foundational mathematical work, even if initially abstract, can provide the indispensable language for future scientific breakthroughs. Christoffel's legacy extends to the profound conceptual shift he facilitated in geometry, enabling a deeper and more accurate description of reality. His work remains a testament to the power of abstract mathematical inquiry to unlock the secrets of the physical world, providing the essential language for understanding a universe where geometry itself is dynamic and intertwined with matter and energy.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.